Hello everyone, a very good evening, or a good afternoon. So I hope I'm visible and audible. So let's wait for 5 to 10 minutes so that everyone can able to join the session. Okay, I have class, so you can sit there. You can close this. So yeah, hello everyone. Let's start the session. So my name is Pooja Verma. I am PMRF Research Scholar from IIT Kharagpur, and instructor for this course is Professor Shantanu Chattopadhyay, Electrical and Electronics Engineering Department, IIT Kharagpur. This is a extra session for, or you can say recap session for your practice. So this is a practice session, you can say that. So this is a practice session on digital circuit. So I hope you have gone through this all week video lectures and you have understand and practiced question well. So this is the outline of whole course. These are the topics which have been covered in brief for this course. So I hope you have gone through. So in this session, we will solve some more numerical problems which is related to gate, or it is a important for your exam point of view also. Okay, so let's practice some more questions. So and also you can use the chat box, and otherwise you can unmute yourself for asking and interacting the questions. Okay, so let's move from the first questions. So first question is the minimum number of two input NAND gates required to implement two input XOR gate. So how much minimum number of NAND gates, two input NAND gates are required to implement XOR gate? So this one is also just related to logic gate problem. So you can answer in the chat box. You can try this question. I hope you have solved this type of question. Please answer in the chat box or try to solve it. Then I will solve it. I will explain it. Okay, nobody wants to answer this question. 4. Okay, it's 4 to input NAND gates, right? Not option 4. Yeah, correct. Okay, so let's see how we can solve this problem. So the minimum number of two input NAND gates are required to implement two input XOR gate. First, we will see what is it XOR gate and what is its logical expression and truth table, how we can represent it. Okay, so this is a two input XOR gate. This is a logic diagram. So two input XOR gate is represented by this A XOR B, where A and B are the inputs and Y is the output, and it is also represented by A dash B plus A B dash, right? Now we will see the truth table of the XOR gate. Truth table. So A and B are the inputs and Y is the output. 0 0 input combinations are 4 for two input. Already we know that, and we have already studied about that XOR gate. When the inputs are same, that it produces output 0, otherwise it will be 1 if inputs are different, right? So this is a truth table for a XOR gate. Now we have to implement this function, right? So how many NAND gates we require? So let's see. First we are taking the two input NAND gate. This is logic diagram of NAND gate A and B. We will get here A, B dash, right? Now, if we further, but we need this expression. from here, then what we will get here? A into AB dash, right? Okay. And similarly, we will again take here one NAND gate and connect it to other input to the B. So here we will get B into AB test, right? Okay, so I'm removing it from here. Now, if we give these both NAND gate output to the another NAND gate, then what we will get? First, we will solve this expression. Okay, so what we will get here? B dash plus AV, right? If you remove that dash or bar from here, similarly here we will get A dash plus AB. Now, the final expression like this AB and another one is B dash plus AB whole dash. Now we will solve this expression, then we will see whether we are getting the expression of a XOR gate or not. So A dash plus AB dash plus B dash plus AB dash. Okay. Now again, if we remove this one, then we will get A, right? A double dash into AB dash plus B double dash plus AB dash, right? Here, what we will get? A into, if we again remove this one, and we will get A dash plus B dash. Similarly, in the next step also, plus B, B, here it is not a plus, it is a into, right? B into A dash plus B dash, right? If further, if the A dash will be 0, right? A and plus A B dash, similarly B A dash and plus B dash will be 0. So what we will get final expression? A B dash plus A dash B, or we can write it A dash B plus AB dash. So this is the expression of XOR gate. So how many NAND gates we are required? That is 1, 2, 3 and 4. So total 4 2 input NAND gates are required to implement 2 input XOR gates. So that's why option 1 is the correct answer for this question. Okay. Okay. So moving to the next question. So in the next question, in the circuit shown, diodes are diodes are ideal and the inputs are 0 volt for logic 0 and 10 volt for logic 1. So what logic gate does the circuit represent? So this circuit, which logic gate it is representing? Whether option 1 3 input OR gate, option 2 3 input NOR gate, or option 3 3 input AND gate, or option 4 3 input XOR gate. So would you like to try this question? Okay. So this circuit, which logic gate this circuit is representing. So already we know that what is a AND gate. AND gate. So when both any of the inputs are 0, then output will be 0. If both the inputs are 1, then output will be 1, right? And in the OR gate, what is it? Truth table for OR gate. Can you tell in the chat box what will be the output for the OR gate? 0. It is a simple addition. 0, 1, 1, 1, right? Yeah, Vaishali. And an OR gate opposite to the OR gate. And the XOR gate truth table already we have seen in the previous one. Okay. Yeah, correct, Vaishali. So, so these are the diodes. So when diode is on, in that case, it could be replaced with a short circuit. Otherwise, it will be replaced with the open circuit. Okay. So if these inputs E1, E2, and E3 are 0 volts, right? So in that case, the diode will be open because it is connected in the reverse bias mode, right? So corresponding diode will be on if it is a 0. All are 0. Okay. And in that case, here supply is also going here. So output we will get 0. Okay. But when all the diodes are off, that means E1, E2, E3 both are in logic 1, or we can say that here we are giving the output 10, right? In that case, no, it's not a OR gate. Okay, we will see. So in that case, diodes are off, right? And the current across the that 1 kilo ohm resistor will be 0, and V out will be 10 volt. So let's check from the truth table. So E1, E2, and E3 here corresponding output. So corresponding input combinations 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, triple 1, right? So what I have told, when the E1, E2, E3 are 0, any of them or any of them, then that's diode will be on, then current will be flow from here to here. Okay. So if any of the inputs are 0, then in that case the output will be 0, right? And when the both three of the inputs are at logic 1, in that case that will be diodes will be off. There will be no current will pass to this. The current through the resistor will flow, and this voltage will appear here. So 10 volt, and 10 volt represents the 1. Okay. So this will act as a, in that case, AND gate, not a OR gate. Okay. So this circuit will act as a AND gate, not a OR gate. 3 input AND gate. Okay. So I hope you understand this question. Yeah. Have you understand? Okay. Okay. So moving to the next question. So next question in the output of a combination circuit given below. What will be the output of this combination circuit? Can you solve it and answer? I will solve it. Uh, I will solve it also. So what will be the output of first AND gate? First AND gate. This is a simple AND gate. These are the AND gates and these are the XOR gates, right? So AB, and output of this AND gate is BC, right? And what will be the output of this AND gate? That is ABC. And here it will be the BC plus XOR AB, not a plus, XOR AB, BC XOR AB, okay? And here we will get ABC, right? So first we will solve it here, otherwise that expression will be very large. We have to solve it here, okay? And if we directly write it and then you want to solve, then we can also go to, so what will be the final output? A, B, C XOR with this part, AB XOR BC, right? This one is final one, but we have to solve it further. So first we will solve this one. So I will write it like this: AB XOR BC, right? So AB dash this, because this one is this is this is only one. So AB XOR AB dash plus AB dash BC plus AB BC dash. Okay. If we further solve it, so A dash plus B dash BC, and similarly this side AB B dash plus C dash, right? Now if we multiply A dash B C, and if we multiply in this part, so B dash will be cancelled out, that will be 0. So and here also B dash will be the cancelled out, it will be the 0, and then AB C dash. The final what expression we have got from there: A dash BC plus ABC dash, right? Now we can put it here so that it is easy to solve it. ABC XOR with this part, A dash BC plus ABC dash. Now if we further solve it, A B C dash plus into this part, A dash B, right? This will act as a one component, this one is another one. So ABC dash, and in multiplication A dash BC plus ABC dash plus opposite one, so ABC A dash BC plus ABC dash, right? This one. So after this I am taking it here from here to here, okay? So if we further like expand it, so it will be A dash plus B dash plus C dash, right? And this part, A dash BC plus ABC dash. Here this side also ABC in brackets, in bracket this side what we will get, so A dash BC, and it become multiplication, so ABC dash whole dash, right? Now what will be the next step? Again, we can multiply in this. So ABC, okay, this part, and this part also expanded. So here we can multiply in this, and then we will expand this one also. So we will multiply one by one. So I am not taking this part currently, so I will solve it later. Okay, so first we will solve this part, just multiply. So a dash will be same. So a dash will be same. So a dash bc plus a, and a dash will be the cancelled out, it will be 0. Okay, so plus 0 again, then multiply b in both, then check b dash will be cancelled out, right? Then again it becomes 0, and similarly in this case also b dash will be cancelled out, and similarly in here also c dash will be cancelled out, and here what we will get, c dash, then we will get c dash only. Okay, so here we will get a b c dash. So what final expression we have got, a dash b c plus a b c dash, right? So I am taking this to there, so that otherwise I can remove it from here, and then we can write the final expression. So here a dash b c plus a b c dash, then we will write this part. So I am taking this step here. So a b c, again we have to break this one. So a double dash will be a dash only, plus b dash plus c dash, then multiplication with the a dash plus b dash plus c, right? From here we will get, again we have to multiply in this, then finally what we will get, so abc will be a will be abc only, and here again b dash will be cancelled out, right? So 0, and here it will again c dash will be the cancelled out, will be 0, right? So now this part is completed. Now next part is a dash plus b dash plus c, right? Hello, yeah, okay, I hope I'm audible. So again if we multiply this one to this, a dash will be cancelled out. So what we have got here, abc to a dash plus b dash plus c, right? There it is, this one. So a dash will be cancelled out, and again b dash will be cancelled out, and here a b c into c. So a b c we will get finally, only a b c we have got. So in this part only we have got a b c, right? Okay, so here we can take a common, and then for the a dash we see, if we take common ab here, then c dash plus c will be 1. What we have got, a dash bc plus a b, right? Okay, if we take b common, so what we have got, a dash b plus a, right? What we can write this part, a dash c plus a, what we can write it, I'm removing here so that we can solve it. A dash C plus A. We can extend it. We can write it A dash plus A or C plus A, right? We can write it to this. So it will be one only. What we got? C plus A only. Okay. So C plus A will we will get the final answer. Which option is correct? Okay. So option 3 is the correct answer for this question. Yeah, option 3 is the correct one. So I hope you have understand this question. So moving to the next question. So next question is bulb in a staircase has two switches, one switch being on the ground floor and other one on the first floor. The bulb can be turned on and also can be turned off by any of the switches. It's irrespective of the state of the other switch. The logic of the switching of the bulb resembles option 1 is an AND gate, or option 2 an OR gate, or option 3 an XOR gate, or option 4 is a NAND gate. So this is a very famous practical question. You can answer this question at least. Yeah, at least you can try. OR gate. Uh, okay, we will see. So, yeah, someone else will answer. Okay, so in the question, it is clearly written a bulb in a staircase has a two switches, one switch being on the ground floor and other on the first floor. So the bulb can be turned on and can be turned off by any of the switches. So irrespective of the state of the other switch, the logic of the switching of the bulb resembles. So let the switch at the one of the floor be labeled as A. Okay, and a switch on the other floor may be labeled as a B. Okay, switch A, I can write correctly, switch A, and this one is switch B. Okay, so if both switch are off, you can say turned off, so that in that case light will be turned off, right? If one switch is off and another switch will be on, and another case is one switch A will be on and other switch will be off, and in another case both switch are on. So practically you can check in your home also, if both the switch are are off or on, then in both the cases the bulb will be off only, and if any of the switch is on either on the first floor or either on the ground floor, that then in that case bulb will be on. So this truth table resembles output is XOR gate. So this in that case you can also hear it A dash B plus AB dash. So in that case switch will act as a XOR gate, not a OR gate. Okay. So option 3 is the correct answer. Yeah, Vaishali. XOR gate. Okay. Okay. So moving to the next question. So next question is the output Y in the circuit below is always 1 when option 1 2 or more of the inputs PQR are 0, option 2 2 or more the inputs PQ and R are 1, option 3 any odd number of input PQ are 0, or any odd number of you can say any odd number of inputs are PQR is 1. Okay. So first we will check what is the logic expression of this circuit. So what will be the logic expression here? So here it is PQ dash, right? Here it is QR dash, and here PR dash, right? So PR dash, here PQ dash into QR dash full dash, right? And again PQ dash into QR dash whole dash. So what we will get here finally? PQ dash into QR dash, because these two dash will be cancelled out, and here PR dash, right? Then finally what we will get? PQ dash into QR dash into PR dash whole dash, right? If we further solve it, we will get PQ double dash plus QR double dash plus PR double dash. It will be cancelled out both bar, maybe. So PQ plus QR plus PR the final expression for Y. So just go by options. So first option, if two or more inputs, that means you can take any two inputs or more than that. So P equal to Q is equal to 0. Let's I'm taking two inputs. So there will be 0, this will be 0, and P, Q, and this will be 0. Whole output will be 0. So this one is a not correct option. So they are asking the output Y in the circuit below is always 1 when we have to put it always 1. Now if we take the second option, that means two or more inputs PQR are 1. So P is equal to Q is equal to 1, right? You can check by taking any QR or PR, any you can take it and solve it. I'm just taking one example. Okay, so for P is equal to Q is equal to 1 is equal to for 1, so PQ 1 1 will be 1. Here QR will be 1 into 0 if R is 0, in that case 0, and here if R is 0 or R is 0, so in that, so output will be 1. So option 2 is the correct answer. Two or more of the inputs P, Q or R is 1. Similarly, if any odd number of inputs, so you can say that P, Q, R, 3 inputs, so 1 and 3 will be 0. In that case, output will be 0. Already we have seen that. You can take any of the, and any odd number of inputs R is 1. So in that case, this option can be correct, but this one is the most correct. Okay, always 1. If we extend, in that case it can be a 0. So option 2 is the correct one. Okay, so moving to the next question. Now next question is, consider a 4-bit digital to analog converter. The analog value corresponds to a digital signal of value 0000 and 0001 are 0 volt and 0.0625 volt respectively. For this one, for this one, the analog value corresponding to the digital signal 1111 is what will be the analog value corresponding this value. So from the questions we can see that the increment in the output voltage on the changing just one bit 00002 0001 is 0.0625 volt. Okay, the increment in the output voltage on changing just one bit is 0.06. So hence it is a resolution. We can say it is a resolution. Hence the resolution is equal to 0.0625. Okay, now what is a output voltage in analog to digital to analog converter? Output voltage is equal to resolution into decimal equivalent, right? Now we have to check the decimal equivalent of this one. What is the decimal equivalent of 1111 is, already we know that is 15, right? So what will be the output voltage? Output voltage is equal to resolution to decimal equivalent, so 0.0625 into 15, right? So what will be, if you multiply, you will get? You will get 0.9375. So you can write it 0.93, right? So option 1 is the correct answer for this question. Okay. Okay, so moving to the next question. So this one is very easy. You can try it. A number of comparators required in a 3-bit comparator type ADC is option 1 is 2, option 2 is 3, option 3 is 7, or option 4 is 8. So what, how we can find out the number of comparators in a ADC? Is equal to 2 to the power n minus 1, where n is this one, 3 bit is given. So 2 to the power 3 minus 1, 8 minus 1, that is equal to 7. So total number of comparators we will get is 7. Option 3 is the correct one. Now next question is also related to this same. Here the n is equal to given as a 4, right? So how many number of comparators required? Can you answer? Yeah, 15, right? So yeah, here also the number of comparators is equal to 2 to the power n minus 1. So 2 to the power 4 minus 1, that is 16 minus 1 is equal to 15. Okay, so option 3 is the correct answer for this question. Okay. Okay, so moving to the next question. So next question is also is different. So it is related to FSM, that is finite state machine. So a traffic signal cycles from green to yellow, yellow to red, and red to green. Okay. So in each cycle, green is turned on for 70 seconds, right? So green is turned on for 70 seconds. So we can write it. I'm only write green and 70 seconds, right? And yellow for 5 seconds, and red is 75 seconds. So this traffic light has to be implemented using a finite state machine. The only input to this FSM is a clock of 5 seconds. Okay, the input of this is 5 seconds. Okay, 5-second period. The minimum number of flip flops are required to implement this FSM. Okay, So what will be the total time of green, yellow and red? Total time in that case when green, yellow and red are on. So that is 70 plus 5 plus 75. How much it will be? That is 150 second, right? And clock cycle is given for FSM. Input clock cycle is how much? 5 second, right? Cycle we can write T clock is 5 second, right? So number of clock cycles will be required will be required input clock cycle. We can write it input. Okay, and like writing other by. So it is, we can represent it by n. So total time divided by the total time divided by input clock cycle. Okay, so total time is 150 second and input clock cycle is 5 second, right? So number of clock cycles will be, what will be? 30, right? 30 cycles, right? So in 30 cycles, the number of flip-flops required in 30 cycles, number of, I'm writing flip-flop in short FF, required is 2 to the power n must be greater than equal to 30 in order to find out the number of, where n is the number of flip-flop, right? This n. So how much? It is 2 to the power 5. In that case, this condition will be satisfied. So n will be 5 in that case. So number of flip-flop will be 5. So flip-flop is equal to 5 to implement a FSM. Okay. So in that case, option 1 is the correct answer for this question. Okay. Okay. So I hope you are getting these questions and understanding. Okay. So okay, so moving to the next question. So next question is, in the latch circuit shown, the NAND gate have non-zero, okay, but unequal propagation delay. The present input condition P and Q both are 0. If the input condition change simultaneously, that is to P and Q is equal to 1, then what will be the outputs X and Y? Okay. So let's say it is a NAND gate 1, it is a NAND gate 2. So let's assume that this is a propagation delay of first NAND gate is less than the propagation delay of the second NAND gate. Okay, X changes state first, then Y changes its state. So first output of X, where here it is said that P is equal to 1, and in that case P is equal to 1, and Y, let's assume that pi is equal to 0 because we don't know what is it. Initially the outputs are 0, right? So what will be the P is equal to 1 and it will be, output will be 1 in the first case, right? Now next output, that means Y is here Q is equal to 1, and here we can say that this first output X is equal to, here we have got 1, right? What will be the output? In that case, 1 1 is 0, right? Now you can check for the second output. Similarly, by taking the first output, you will get either 1 0 or 0 1 you will get. Okay, so in that case, option 2 will be the correct answer. You can check it very normally also. You can take p is equal to 1, q is equal to 1 and take x and y initially 0, then you can calculate the x and y, you will get 1 0 or 0 1. So either x is equal to 1, y is equal to 0, or x is equal to 0, y is equal to 1. Okay, so option 2 is the correct answer in that case. Okay, so moving to the next question. Now next question is, consider a D latch shown in the figure, which is transparent when its clock input Ck is high. Okay, and zero propagation delay. In the figure, the clock signal CLK1 has a 50% duty cycle. Okay, and CLK2 has 1/5 period delay version of clock 1. Here it is given. It is the duty cycle out at the output latch in percentage. What will be the duty cycle in the output latch? Okay, so duty cycle of a waveform we can find out by duty cycle is equal to T on divided by T. Already we know that. So the output of a D latch is high when both the input clock 1 and clock 2 are high in this period, or we can say that till here it will be high from here to here. Okay, and the output waveform is and condition of the two clock input. Okay, so here it is given, so we can divide it further also. Here, then here, 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 then output you can see that is a clock 1. Okay, here, then it is here, here. You can remove it again. Draw this one. So just check. Is there any issue? Okay, we will get like this. So we will check for the output where it will be high. So here, in that case, here to here, right? It will be high. Again, it is here, it is low, it is high, it is low, it is low. So it will be the 0 till here. Again, it is 0 till here. Again, it is high in this period. So I can draw it lightly. Okay, here. Now again it will be 0 here, 1 here, so it will be 0, right? So this is a output. Okay, so it is a total clock, which is a T by 5. So at T by 5 it will be off, and T clock by second is only on. In this period is only it is on. Okay, so now we can write for the on time only. Now the on time will be T on is equal to T clock by 2 minus T clock is a clock by 5. Okay, so we will get 3 T clock by 10 if you solve it. Okay, so the duty cycle is, you can T on divided by T, right? So T on is 3, T clock by 10 by T clock, total time duration T clock into 100, because they have asked the duty cycle and the output lies in percentage, right? So T clock will be cancelled out. So here we will get T by 10 into 100, right? So this will be cancelled out, so 30% only. Okay, so that's why option 2 is the correct answer for this question. Yeah, Yamuna, this is 30%. Okay, so I hope you understand this question. So moving to the next question. Okay, so next question is, a mod n counter using a synchronous binary up counter with synchronous clear input is shown in the figure. The value of n is, so here we can see that the clear output of this NAND gate is going to clear. That means after this counting state, it will be like a clear output. So it is a clear R is a active low signal. It is activated when clear. This will be 0 and reset the flip flop in that time. Okay. So from the given sequential circuit, the clear output is going to the, what is it, QB into QC dash, right? QB QC dash is the going to the clear input, right? That means when both QB and QC is equal to 1, then clear will be 0, right? Otherwise clear will be 1. So just check for every clock pulse. It is a clock. Here the different outputs QA, QB, QC and QD. And here we can write the clear output, right? So 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 triple 1. I will write it later if required. So at the first clock pulse, these are the number of clock pulse when we are giving. Okay, so QB and QC dash. Okay, 0 0 will be 0 0, both 0 and dash 1. Here it is also, if you Q and other we didn't take as a input QA and QD, so only we can check QB and QC dash. Okay, so here it is again 0 0, so 1 0 1 0 0 dash 1, right? Here also 1 0, in that case also, here also it will be 1. Here in that case, let's see, 1 1 1 and 1 dash will be 0. Okay, again here it is 0 and all other cases it will be 0. So how many states it is activated or it will be clear after this one? That means after 6th clock pulse, or you can say that at 7th clock pulse, at 7th clock pulse, the output of the counter will be reset. Output of the counter will be reset. Okay, so mod of the counter is mod of counter is 7. Okay, so n is equal to 7, because after 6 clock pulse it will again start counting 0 to 6. So total number of states will be 7, 0 to 6. Okay, so option 1 is the correct answer for this question. Okay, so I hope you understand this question. So moving to the next question. Okay, the next question is, given JK flip flop 5 JK flip-flops are cascaded to a form circuit shown in the figure. The clock pulse at a frequency of 1 megahertz applied. That means input clock pulse frequency is 1 megahertz. Input clock pulse frequency is 1 megahertz. It is given. The frequency in kilohertz of the wave form at the output Q. At Q3, at this, what will be the frequency? Okay. So here we can say that here if we count at each flip-flop, so Q0, Q1, Q2 and Q3. So for n is equal to 4, that means for fourth flip-flop the output frequency is, we will taking the output frequency at Q3, so that means at fourth flip-flop, right? Frequency. Okay, so it is calculated by input frequency divided by 2 to the power n, where n is the number of flip-flop. Okay, n is the number of flip-flop. Okay. Okay, here n is the number of flip-flop. The input frequency is given, so output frequency we can write like this: frequency at Q3. It is better for understanding. Frequency at Q3 is equal to input frequency is 1 megahertz and number of flip-flop is 2 to the power 4. That means 10 to the power 6 divided by 16, right? If you further solve it, you will get, you can write 1000 because we need in kilohertz. Just save it in 16. So you will get 62.5 into 10 to the power 3. You can write it 62.5 kilohertz. Okay. So frequency at Q3 is 62.5 kilohertz. Okay. Okay. So I hope you are understanding. So you have understand this question. Can we move to the next question? Okay. So moving to the next question. The next question is in DRAM, dynamic RAM, you can say that option 1 is periodic refreshing is not required. Option 2 is information is stored in a capacitor. Option 3 is information is stored in a latch. Or option 4, both read and write operations can be performed simultaneously. So option 2 is the correct answer. In a DRAM, information is stored in a capacitor because this is a basic diagram of a DRAM. So in a DRAM, capacitor to store a bit of data is used along with the MOSFET transfer device, which acts as a switch. Transfer here, MOSFET will act as a switch and capacitor is stored for a data. So in a DRAM, periodic refreshing is required because capacitor needs a refreshing. Then information is stored in a capacitor and both read and write operations cannot be performed simultaneously. Okay, so that's why option 2 is the correct answer. Information is stored in the capacitor. Okay, here this option is not correct. Periodic refreshing is not required. It is written, but periodic refreshing is required for a DRAM. Okay, here we are using the capacitor, not a latch. So information is stored in a capacitor. Okay, and also read and write operations simultaneously cannot be performed at a time. Okay, option 2 is the correct answer for this question. So moving to the next question. So a 16 kilobyte, or you can say it's equal to 16,384 bit memory array is designed as a square with an aspect ratio of 1. Number of rows is equal to the number of column. Okay, you can say that number of row is represented by m and number of column is represented by n. The minimum number of address lines needed for a row decoder. Okay, so the size of a memory register is given by the size of memory array, you can say that, is given by m cross n, where m is the number of rows and this one is a column. Okay, and it is also given the array strength as a square, that means m is equal to n. Okay, where m is the number of rows and n is the number of columns, and now it is given the array is size of square, that means number of rows and number of columns are equal. So we have the memory array, we have 16 KB, that means m cross n, so that means if m is equal to 1, so m into m, so that is written as a m square, and it is equal to 16 KB, or approximately equal to 16,384 bits, right? Now m square is equal to 16,384 bits. If you again to solve it, m is equal to, you will get 128. You can solve it. Okay, just check what will be the root of m. So you will get m is equal to 128. Okay, so now the rows are faced by address lines and all the registers of a particular row handled by a data line. Okay, so now register with 128 flip-flop can be handled by, now we need to find out the number of flip-flop or number of storage devices. So for the particular, for this 128, the number of flip-flop can be handled by log 2 m. So what will we get? Log 2 128. If you further solve it, you will get 7. That is a data line. Okay. Similarly, the number of address lines required by a row of decoder. Number of address lines required for the decoder is 7. That is 7. Okay. This option 2 is the correct answer for this question. Okay. So I hope you understand this question. If you have any doubt, you can ask. Otherwise, we can move to the next question. Can we move? Okay. So moving to the next question. So a new binary coded pantry BCP number system is proposed in which every digit of a base 5 number, okay, every digit has a base 5 number, is represented by its corresponding 3-bit binary code. Okay, for example, the base 5 number 24 will be represented by its BCP code is 010 and 100. In this numbering system, the BCP code 1000 100 11001 corresponding to the following number system in base 5 system. What will be the corresponding number in base 5 system? So here it is given base 5 number is represented by its corresponding 3-bit binary code. So let's make a group of 3 bits. So 3, 3, 3 and 3. It is a base 5. Okay. So example 2 is represented by 0, 1, 0 and 4 is represented by here 1, 0, 0. So here it is a 1, 0, 0. So that means it is represented by 4, and it is a 0, 1, 0. It is represented by 2. Here that means it is a 4, it is a 2, it is a 1, right? So here it is a 2 and 1 is 3, and here it is a 1. So corresponding base 5 number system is 4231 for this BCP code. Okay, 4231. Okay, option 4 is the correct answer for this question. Okay. So I hope you understand this question. So moving to the next question. So next question is basic from the K-map. Following is the K-map of a Boolean function with a 5 variable, that is P, Q, R, S and X. The minimum sum is, what will be the sum? So how it is here it is given, it is for x is equal to 0, it is for x is equal to 1. K-map for x is equal to 0 and x is equal to 1. So how we can solve it? So first we will solve for this. It is given, that means for every variable or every sum, or you can say that every variable, the x dash will be multiplied. So x dash for first K map I am writing for x dash, x is equal to 0, so we will write x dash. Okay, so just make a grouping. So here we can make a 4 group of 4, right? That means chord, and no other ones are there, so just make a group. So it is, what will be the expression for this one? So here we can take common 1. So 1 means S, right? And here for this column wise, 0 is common. So that means Q dash. Similarly, here it is written for x is equal to 1. That means only x. Now here also it is making the chord. So what will be the common in both? 0. Here in this row wise 0. So that means S dash, and column wise 1. Common is 1. So Q only. So answer is, if we write it, Q dash S x dash plus Q S dash x. Okay. Which option is correct? So option B is the correct answer in that case. Okay. So moving to the next question. Now, next question is, for the ring oscillator shown in the figure, the propagation delay for each inverter is 200 picosecond. Propagation delay for each inverter is 200 picosecond. What is the fundamental frequency of the oscillator output? What will be the frequency of the oscillator? Okay. So how we can solve it? So in order to find out the propagation delay at the output, formula is T is equal to 2 N T P T. Okay, where T is the time period and N is the number of inverters, and TPD is the propagation delay associated with each inverter of each inverter. Okay, and 2 is multiplied when the inverters are connected in feedback. Okay, so here inverters are connected in a feedback, so here 2 multiplication will be there. So let's take T is equal to 2 into number of gates are inverters are 5, and propagation delay for each inverter is 200 picosecond. So what will be the, so it's a, right, 2000 picosecond, right? Or you can write it 2 into 10 to the power minus 9, or you can say that 2 nanosecond. Pico means 10 to the power minus 12. Nano means 10 to the power minus 9. Okay. So now we have to find out the what will be the fundamental frequency. So already we know that fundamental frequency f is equal to 1 by t. So 1 by 2 nanosecond, you can just write it 2 to the power 10 to the power 9 divided by 2. So we can write it like this, 10 to the power 6, right, by 2. So 500 megahertz we will get. It is 10 to the power 6 is represented by a megahertz. Okay, so 500 megahertz is the correct answer. Option C is the correct answer for this question. Okay, so I hope you have got this question. So moving to the next question. Yeah, so anyone have any doubt, or we can move to the next question? Okay, so moving to the next question. A memory system has a total of 8 memory chips, each with 12 address lines and 4 data lines. Okay, the total size of a memory system. What will be the total size? So total size of a memory is can be find out by a memory will be there are n into d means data lines, and 2 to the power 8 means this one is address lines, data lines on number of total 8 memory chips. The number of chips memory chips, so 8 into 4 data lines 4 and 2 to the power 12. 12 is the address lines. Okay, if you further multiply it, you will get 131072 bits. Okay, if you further convert it, you will get 16k bytes. Convert bits into a byte, you will get it. Okay, approximately 16 kilobyte. So just you have to multiply, and after that you have to convert into a byte, because in the question options they have given in bytes only. Okay, so 16k bytes. If you convert it, just divide by 8. Okay, okay, so I hope you are getting. So moving to the next question. Okay, so next question is, an input output peripheral device shown in the figure below is to be in interfaced to an 8085 microprocessor. To select an input output to in an input output address range D4H to D7H, so that means H means hexadecimal, its chip select should be connected to the output of the decoder. At which output of the decoder is connected? This is shown in the figure. This chip select should be connected with output of the decoder. These are the outputs of the decoder. So address range is given, that is D4 to D7. So what will be the address lines? That is A7, A6, A5, A4, A3, A2, A1 and A0. So address line D4 means D means 13, right? 1, 1, 0, 1, right? And 4. So 0, 1, 0, 0. So it is a representation of D4. Now the next is range is D7. So D7 1, 1, 0, 1, 0, 1, 1, 1, right? So here what are the inputs? A2, A3 and A4. A2, A3 and 4. What is the decimal equivalent of A2, A4? So it is a 5, right? So output 5 should be connected to its chip select. Okay, that means output 5 is connected to the chip select. Okay, just we need to check the are the input combinations are there in this address range. So this is the 5, right? 415. Okay. So option B is the correct answer for this question. Okay. Okay. So I hope you are getting. So moving to the next question. Okay. The next question is a 16-bit triple carry adder is realized using 16 identical full adders. Okay. As shown in the figure, the carry propagation delay of each full adder is carry propagation delay of each adder is carry propagation delay of each adder is equal to 12 nanosecond, and the sum propagation delay propagation delay is 15 nanoseconds. So in worst case delay of it is 16-bit adder will be. So already we know that the carry is propagated to one full adder to the next full adder, but some is not propagating. Some will be adding, right? So 0 to 15, the carry will be propagated to 0 to 14 only, 0 to 14 full adder. So that means 14 into 12 nanosecond, because carry will be propagated not after 14, it will not be propagated, it will be the final one, right? So what will be the total propagation for the carry? Total propagation delay for carry will be 14 into 12 nanosecond, right? So what you will get? 0 to 15, that means 16 full adders are to, so it will be 15, right? 15 into 12, you will get 180 nanosecond. But some propagation delay will not propagated, some propagation delay will be only 15 nanosecond, right? So worst case propagation delay will be delay will be 180 nanosecond plus 15 nanosecond, so 195 nanosecond. So worst case delay of this 16-bit full adder will be the 195 nanosecond. It is given in nanosecond. So 195 nanosecond. So already we know that only carry will be propagated from one full adder to another, but some will not propagated. Okay, so that's why it is multiplied by each stage. 15 into 12, total propagation for carry is 180 nanosecond, and some propagation is 115 nanoseconds only. Okay. Okay, so I hope you understand this question. So moving to the next question. Okay, so next question is a 4-bit ripple counter and a 4-bit synchronous counter are made using flip-flop having a propagation delay of 10 nanoseconds. Okay, if the worst case delay in a ripple counter and synchronous counter be R and S respectively, then so it is a n is equal to 4 because it is a 4-bit ripple counter and 4-bit synchronous counter. Okay, so for the worst case the ripple counter, it is represented by R, right? So in the ripple counter the delay will be propagated by n into TD. Okay, so n is given 4, number of flip-flops are 4, and TD is given as a propagation delay for each flip-flop is 10 nanosecond. That means for ripple counter worst case delay is 40 nanosecond, and for synchronous counter, yes, counter, it's counter, that means S. Clocked are simultaneously given, so the worst case delay will be TD only, that means 10 nanosecond only. So ripple counter worst case delay is 40 nanosecond, and the synchronous counter worst case delay is 10 nanosecond. Okay, so R 40 nanosecond and S, so option C is the correct answer for this question. The answer is C. Okay. So I hope you understand this question. So moving to the next question. Okay, so moving to the next question. So the minimum number of flip-flops needed to construct a BCD decode counter. What how many minimum number of flip-flops are required to construct a BCD code? So already we know that BCD counter counts only 0 to 9. That means total 10 states will be there for a BCD counter. So in order to find out the number of flip-flops required, m less than log 2 n. N is the number of states here, number of states, or number of m is the number of flip-flops. Okay, so m is greater than log 2. Here number of states are 10 because it is counting 0 to 9, so 10, right? If you take it, you will get m is equal to 4. Okay, so 4 flip-flops are required to construct a BCD counter. Okay, so option 2 is the correct answer for this question. Okay, so I hope you understand. So moving to the next question. Okay, so next question is, the synchronous sequential circuit shown below work at a clock frequency of 1 gigahertz. The throughput in megabits per second and the latency in nanosecond respectively. What will be the throughput and latency? That means delay. Okay, so it is the given circuit serial in, serial out, right? And the clock frequency is 1 gigahertz. It is given. So latency will be find out by C is equal to n into t clock. So n is the number of flip flop, is the given as 3. The t clock is given as 1 t clock. Here the input frequency is given, f is given 1 gigahertz. So in order to find out t clock, 1 by f, so 1 by 10 to the power 9, gigahertz means 10 to the power 9, so 10 to the power minus 9 second will be there. Okay, so that means it is written as 1 nanosecond. So 1 nanosecond t clock. So total latency will be the 3 nanosecond. Okay, if you multiply, and throughput is calculated by throughput. Okay, so it is calculated by number of bits per second. Okay, so how many number of bits per second? So for 1 bit, the delay will be 1 nanosecond, right? 1 nanosecond. So what will be the throughput? Nanosecond, so number of bits per second. So 1 bit, 1 by 10 to the power 9, right? Minus 9. Now it is per second. So if you further solve it, 10 to the power 9 bits per second. If you further do that, 1000 mega bits per second it is. Okay. So option 1 is the correct answer. The latency is 3 nanoseconds and throughput is 1000 megabits because it is already given megabits. So you can write 1000 only. Okay, 1000 megabits per second. Okay. So I hope you are getting it. If you have any doubt, you can ask. Otherwise, we can move to the next question. Anyone of you have any doubt, or we can move to the next question. Okay, so moving to the next question. So next question is determine F max for a 4-bit synchronous counter if TPD for each flip-flop. TPD for flip-flop. I'm writing here 50 nanosecond and TPD for AND gate is 20 nanosecond is given. Determine the F max for a 4-bit synchronous counter if TPD for each flip-flop is 50 nanosecond and TPD for each AND gate is 20 nanosecond. So what will be the total delay? Total delay is TPD and flip-flop and TPD PD flip-flop plus TPD and gate. That means 50 nanosecond plus 20 nanosecond. Total 70 nanosecond. Okay, and F maximum can be find out by 1 by total delay. Total delay. So 1 by 70 nanosecond. You can write it 1 by 70 into 10 to the power minus 9. Right? If you further divide and solve it, you will get 14.3 10 to the power 6, or you can write it 14.3 megahertz. Okay, so option 4 is the correct answer. F maximum will be 14.3 megahertz. Okay, so these are the questions or practice question for this session. So now if you have any doubt, you can ask. Otherwise, we can close the session. So okay. Thank you everyone. Thank you for joining this session. Now if you have any doubt, you can ask. Otherwise, we can close the session. Now it has been completed. Anyone of you have any doubt regarding the session or anything? Questions? Okay, no doubts are there. Okay, so now if you have any don't have any doubts, so now we can close the session. So okay, thank you everyone. Thank you for joining this session and this course. Okay, now you can leave the session. If you don't have any doubt, you can leave the session. what will be the pattern of question? That can be a multiple objective types and fill in the blank type questions are there. And maybe you have to solve, is it online or offline? It depends. All 2 mark questions, that I don't know because I think faculty will communicate regarding that. What will be the question, and maybe it will be 1 mark question will be there also. Okay. Yeah. Okay, Dina. So, you have any doubt to related to any questions, anything? Okay. Thank you. Thank you, everyone. Thank you for joining this session. Okay. Now we are closing this session.